Hello and welcome to Through the Telescope, the podcast that puts the lens on astronomy. I'm Rose Waugh and I'm an astrophysicist and science communicator.
And I'm Elliott Bruce, and I'm neither of those things, but I'll be trying to find out why we should even care about astronomy. We'll be exploring some of the big topics in the field in little manageable pieces and have some fun along the way.
So, whether you know your red giants from your redshifts, or you're not quite sure what the difference between astronomy and astrology actually is, join us as we launch ourselves into the cosmos and try not to burn up on re-entry. Through the Telescope is sponsored by Pic Astro, the astronomy and astrophotography image sharing app, dedicated to your images of the cosmos no matter what stage you are on your journey around the universe. No ads, spam, or fake accounts.
So, Ro, today we're talking about centaurs.
Indeed.
Apologies if you can hear some background noises. We've got our dog here, and she might intermittently decide to make a ruckus.
I'm not sure she has much to contribute to the podcast, but she probably thinks otherwise.
Not so much. So, centaurs are things that I am vaguely aware of existing, basically as a name, before this episode, but no idea what they actually are. So, what are they?
You're not really alone there. Well, there are lots of different definitions, so that's part of the reason probably that you don't know what they are.
Okay.
They're basically things that float about near the outer planets of the solar system, kind of in those orbit ranges. So they're rocky and icy objects that are in a particular region of the solar system.
Right, okay.
That's pretty much what they are.
Right.
Which isn't maybe a particularly helpful definition.
Yeah, I guess we don't really have lumps of gas floating around in the outer solar system, except for, like, the planets. So, things that are floating about are rocky or icy, as it were. So it's basically just debris, I guess, in a certain region. Is that fair?
Yeah, it's debris. Yeah.
Nice.
They're pretty small, really, because, most of the material that would have been around there has been coagulated into the planets.
Yeah.
So they're pretty small. They have kind of comet behaviour.
Okay.
But also asteroid behaviour.
Right.
And some centaurs are comets.
Okay.
And some are asteroids.
Is that like, it kind of depends on who you ask? Or, well, I guess it does if some people have different definitions of a centaur in the first place.
Yes. I kind of got the impression that more of the overlap comes from how one defines the word centaur.
Right, okay. I see.
Because you can, as we've established lots of times already, you can, when you're classifying things, there are always things outside of the boxes that you have made, and if you try to reclassify under similar physics or whatever and have different boxes, then you find different things outside of your boxes, and you can never really quite get everything to...
Yeah, you either exclude different things from your box, or you find out that you've added too many things to your box,
Yes.
and it's no longer really a helpful box anymore.
Exactly. So
Jupiter becomes a centaur.
yeah, and then you're in trouble.
So the first one was discovered by Walter Baade, a German astronomer, in 1920, but he didn't know it was a centaur because they didn't exist yet.
Yeah, that is how a lot of things in astronomy work.
Yeah. So it's called 944 or maybe Hidalgo, who did not know this person. Obviously, what's the word? Ignorant. But he is actually a Catholic priest and revolutionary leader of Mexico and regarded as the father of the Mexican nation.
Wow. I am ashamed to say I didn't know that either.
Miguel Hidalgo y Costilla.
Nice.
So, yeah. He ends up being executed. Like, I think you kind of have to be if you're a father of a nation. A martyr.
Yeah. Is there a reason?
So I wasn't...
They named it after him?
I wasn't entirely sure, but what I did see was, like, a couple of years later, a bunch of German astronomers had gone over to Mexico to view a total eclipse. And they met the Mexican president and asked, can we name this thing after the founder of Mexico, as it were?
And they were like, yeah.
They're like, yeah, I wasn't expecting this. But
okay, right.
There didn't seem to be any further reason. So
well, okay, that's interesting.
Yeah, and that's orbits between the asteroid belt and Saturn's orbit. But it wasn't until 1979 when the American Charles Cowell discovered 2060 Chiron, which is named after a centaur in Greek mythology.
Mm-hmm.
And he thought it's half asteroid, half comet. So that's like a centaur.
Yeah.
And then lots of people afterwards have then named their things that have fallen into this category after centaurs in mythology.
Yeah.
I didn't know that there were that many centaurs in mythology. But...
well, neither did I, because there are a lot of centaurs, but I suppose however many of them are just given a number plate, so...
yes, yeah.
Probably doesn't matter if you're only naming the particularly large or somehow inspiring ones.
Mm.
So yes, as we've established, although not very firmly, because it is not very firmly established, the orbits of centaurs typically, they have a reasonable fraction that is between the orbits of Jupiter and Neptune. But the definitions do vary.
Yeah.
Depending on who you ask. But normally the closest approach to the sun, or the perihelion.
Yes. Okay, yeah, that's a word.
Or,
okay,
this is part of the different definitions, or the semi-major axis is between those of the outer planets. So Jupiter to Neptune.
Right. Yes. Okay.
But they don't necessarily, they don't have like circular orbits.
Right, okay. Okay.
So their furthest approach from the sun, or the aphelion, is going to be further out than that.
Yeah, so when we think of... you could easily think, oh, well, let's just define it based on its orbit. That's easy. And then you're like, well, do you want the closest approach to the sun, the furthest approach to the sun, the average?
Exactly.
What kind of average?
Yeah.
Yeah, okay. I see.
Yeah.
I see.
And their orbits can... Some of them have very stable orbits.
Okay.
But they can have pretty unstable orbits as well. So you can also have definitions based on how stable is their orbit, in which case you then say, well, these ones aren't Centaurs anymore because they're very stable orbits, but they were Centaurs to...
Somebody else is like, yeah, but in like 100 billion million years, it will have gone. And somebody else is like, no, it's only like 100 million years. After that point, if it goes after that, it's pretty stable. Or whatever. That kind of thing.
Yes. And you can imagine how exciting these discussions at conferences would be.
Yeah. Yeah. I thought, I know. The IAU.
Oh, no.
They're the people
Yeah.
that decide everything. We, as the podcast goes, we are try to follow the IAU definitions of things, generally speaking, right?
Yeah, I mean,
It's generally the accepted
they're typically
thing, right?
accepted, and lots of working astronomers and astrophysicists are members of the IAU. So it's not as if they're completely far removed from this, the working science or anything.
Yeah. And
they can be quite behind the times for some things, but
which is generally because they've got like how many people that have like contradictory views on things all on the same committee.
Yeah.
Thrashing it out.
It's committee work.
And
so
that's also the case here, so they don't really, they've got kind of fudge as to Centaurs, so they weren't very helpful.
That does not surprise me in the slightest. And some of them are weird and orbit in retrograde. Most of them don't, but some of them do.
So does that mean they then go round, if all the planets are going round clockwise or anti-clockwise, I guess, depending on whether you're above or below, it's going in the opposite direction round the sun?
Yes.
Okay. Does that mean anything?
There have been suggestions that it might indicate an interstellar origin.
So is that if it comes from within our solar system, generally speaking, conservation of angular momentum means that everything goes around the same way, generally speaking.
Yeah.
So if it is going the opposite way, then it's quite possible that it doesn't come from our solar system.
Yeah, it could have got captured by the sun, or I don't know. I guess it could have had some interaction that has forced it to then somehow orbit in the other direction. I don't know how much energy you would have to give an object for it to reverse its orbit.
Yeah.
Pretty extreme, you would think. And also manage to do that whilst not completely flinging out the solar system.
Yes.
But I can't personally comment on how likely that would be. I think they are still somewhat a mystery of the solar system.
Love a mystery of the solar system.
What do you think, Papa? I only like mysteries that have food.
So it seems that the general sort of consensus in a lot of these things come from the Kuiper Belt and beyond from our solar system, and have then sort of worked their way in. Or they've come about from other things being smashed together.
Yeah.
But I guess that's sort of how they got to where they are. But where are they going?
Wow. Unlike things like the planets, which are in our solar system and very much not going anywhere, their orbit is very stable, and they're going to stay where they are the rest of the solar system. It's life. Centaurs are still trying to find their place, really. So some are kind of transitioning from being trans-Neptunian objects to becoming comets,
Okay.
which maybe isn't that much of a surprise given that we already talked about how they have some comet-like behaviour. There have been suggestions that Ceres, the dwarf planet in the asteroid belt,
Well
could
versed
have...
in
yes,
Ceres.
you are. Could have once been a centaur.
Okay.
That was then, thrown about the solar system and came to rest in the asteroid belt.
And that's kind of why it is so much bigger than other things in the asteroid belt. Is that kind of the...
I guess that is the suggestion from that camp. Yeah. But really, the discovery of the centaurs as a class of objects, however you choose to classify them,
Whatever they are.
whatever they are, has combined with active asteroids, which are asteroids that have tails.
Okay, so Comet's got like a tail of stuff being thrown off it, and these are asteroids that have the same thing.
Yes, but they don't go beyond Jupiter.
Oh,
They
okay.
stay
Okay.
in the inner solar system. It's kind of blurred the distinction completely between what a
Yeah.
comet is and what an asteroid is,
I can kind of
which
see that.
previously felt very, or at least relatively distinct,
Yeah.
and now less so, which is maybe not a surprise. We like to box things,
Yeah.
but that's not necessarily how things are in reality. They're just boxes that fit our needs or whatever. And sometimes these distinctions don't really have such kind of physical meaning.
And I guess when you say physical meaning, that's not just necessarily how they behave, but also maybe where they came from in the first place.
Yes, exactly. Just kind of everything about them, really.
Yeah. Okay. Yeah. Yeah.
So yeah, and equally, one of the moons of Saturn, Phoebe,
Phoebe.
who I kind of think of them as like not people, but do you know what I mean? Like,
But it also doesn't help when Phoebe's actually somebody's name nowadays.
it's aggravated by the kids' addiction to planets, dwarf planets, solar system bodies in general, and personifying them.
Yeah.
And it's seeping into me. Phoebe, who was discovered by William Pickering, which we talked about in...
Still a classification, was it?
I think it could have been, yeah. Might be a captured centaur as well.
Okay.
Which is pretty cool. And also kind of less weird because Saturn is within that kind of region, so it kind of makes... well...
And also Saturn's got a whole load of moons. So
Oh, yeah.
if any
Moons
of
for
them,
days.
if any of the planets are going to have a moon that is also maybe once a centaur roaming around,
Found its new home with Saturn.
So I guess we think a lot of moons formed early on in the solar system, kind of similar time to when the planets did. Is that kind of the idea? And this would be like later, more recent.
Suppose it depends on how you think the moon formed,
Right, okay.
as to when you think it formed.
Or whether it's like two things smashed together. The two things might have come about at the same time-ish as the planets, but then it's more recent, etc., etc.
Mm-hmm.
Okay. So that's when...
So Phoebe was pretty lucky, really. because it got captured by Saturn
It's on its forever home.
and then it stayed there, assuming that that's where it originally came from.
Yes.
But in general, having a very close approach to a large planet of, Jupiter, Saturn, Uranus, Neptune is not necessarily ideal.
No.
You might collide with it if you're lucky. If you're unlucky, you might be yeeted out of the solar system.
Yeah.
So,
Because I guess we use, or have used, like, the larger planets to, like, the Voyager missions used, like, Jupiter to, like, slingshot round towards Saturn. And that's people looking at equations, thinking, how can we do that? And doing the math. Whereas if you just happen to
you don't want to take a random
stray,
stab at it because
Voyager gets thrown wrong way.
Yeah, exactly.
Okay. That's a bit like that. Do you remember what was it called? Oumuamua?
Yes.
The interstellar, potentially, probably, visitor.
Yeah.
Yeah.
I like to think that it was.
Yeah, me too.
But
There's a lot of rocks in space, so why not? That's not a very astrophysics answer.
there's also a lot of space in space there.
There is. I wonder what star it would have come from. Do people say?
So, well, maybe we can do a future episode on that and see how, how things have evolved since then. I've not really been keeping up with the literature, but presumably there is more research that has been done on it since then. We'll have to find out, I guess. In the meantime, back to Centaurs. So, yeah, they're in the outer bits of the solar system, and there are a lot of them, possibly a very lot of them. So, we're talking like maybe 40,000.
Okay.
Or maybe 10 million.
Right. That's quite a big range.
Yes, and that's just for the objects that are greater than 1 kilometre in diameter, which, is relatively small, but still, like,
Yeah.
there's going to be more than that.
Yeah.
Yeah.
Does this come down to, again, the surprise that I've found? Because I kind of figured we've got our own solar system, like, nailed down. We get
We
it.
don't.
Is it just like they're quite far out, really, and they're small, and a lot of them may be quite dark, I guess, and not very reflective?
Yeah, and when you think about, anyway, just how far away everything is, right? I mean, the sun seems quite bright to us.
Yeah.
But the amount of light reaching them, I mean, your luminosity is going like 1/r².
Yeah.
So for every, like, time you double a distance, you quarter the luminosity.
Yeah.
Yeah. So, or, you go 10 times the distance.
And it's 1/100th of
Yeah.
1% of the... Yeah.
So at 1 AU, you have whatever luminosity. At 10 AU, you've got 100th of that. Yeah, you've got 1% of that. So even before you get to, like, what are they composed of? Do they not reflect very much? They're really small.
You're already working with some pretty...
They're already not getting very much light.
Yeah. And I guess also with their sort of weird, crazy orbits as well. Or they can be. Not all of them. But then it's like, you're not even like, let's just look sort of vaguely in the plane of everything. Because they can also be... Woo.
Well, also it can just be hard to know where to look, I think. They're so small. And them, when they're close, when they're at their closest approach, at their perihelion, you might stand a decent chance.
Yeah.
But when they then kind of recede further out into the solar system for a long time period,
Yeah.
you are finding it then even more difficult to spot them. So, yeah. But yeah, the biggest one is about 260 kilometers in diameter.
Okay.
Which is, like respectable. It's even got a ring system. It's the smallest thing that we know of that's got a ring system.
That's impressive. Okay.
So yeah.
So that must be like 120 odd miles or something like that. So it's a geographic distance, as it were.
Yeah.
But it's not, it's relatively small on the scale of things, and it's got rings. Like, it's not like...
It's pretty small, when you think about the fact it's got rings, it's like, oh, that is small.
Yeah.
Like, very small things can have ring systems. Yeah. We have, learned from 10199 Chariklo. I don't know if that's how it's pronounced.
Apologies to any Chariklos listening.
But that's what we've learned from this object. Like, yeah.
Okay.
But at the same time, it's a respectable size for a solar system body, I would say. Feel like when you're talking about things that are like 1 kilometer in size, you're like, okay.
Yeah.
That's like a small human scale. 1 kilometer is like not tiny.
But on an astronomical scale, that's like...
It's a piece of dust in the solar system, really. Whereas 260 kilometers, it's like it's not teeny tiny.
No, but...
Yeah. Again, with the, like, what does size even mean? Everything is relative, so, like...
Well, when I said on an astronomical scale, I was like, astronomically speaking, the sun is insignificant because the universe.
Yes.
So...
Okay, let's move on before we fall down that rabbit hole.
Okay. So what are they made of, then?
Rock. Ice.
Okay.
That's about it. But ice in astronomy does not just mean solid water.
Okay.
Ice just basically means lots of things that are frozen. Okay. Lots of things that have turned into a solid that normally wouldn't be a solid.
So we're not just talking about, like, water ice?
No. But it includes water ice. So there has been some spectroscopy that has been done.
A little bit of spectroscopy.
Yeah. Using light to tell what is inside an object, which chemicals are inside an object. Pretty cool. And they have found various different compounds, including water ice, but also methanol in its ice form, carbon monoxide in solid form, amorphous carbon.
So just carbon that is sort of lumps of carbon.
Just there, hanging.
Yeah.
Tholins, which are a range of organics that are formed from UV radiation.
Okay.
And olivine. Yeah, they can have quite, complex compositions. And also it can change over time, depending on, what they're doing. Are they near the sun? Are they not? Whatever.
Okay, so if they're rocky and or icy, does that mean they're sort of like grey, maybe sort of shiny, whitey kind of coloured?
Generic space rock.
Yeah.
Kind of. You do get bluey grey ones.
Okay.
You also get reddy ones,
Oh, okay.
varying shades of colours. People don't seem to know why. Again, I guess it's another way to potentially classify them, but then you find,
Multiple things going on.
yeah. So, for example, some of the blue ones are known to periodically release gas from being, radiated by the sun from the solar radiation.
Okay. Like a comet, kind of.
Yeah, kind of like active, like a comet with like a tail, and this exposes, more layers of ice that can then be melted by the sun.
Right.
Whatever.
So then it sort of looks like it's covered in nice, fresh, icy kind of layers because it's not been exposed to space. Whereas, but if you left it for a longer time, it might not be like that sort of pristine ice color, whatever that is.
Maybe,
in these.
maybe. But then some of the active centaurs are red.
Right. Okay. So scrap that, but don't scrap it because sometimes it works.
Science.
Okay.
The different colours could maybe mean different origins, or it could mean that they've had different kind of life events in a certain order.
Right.
Or it could mean that they have been exposed to more radiation or less radiation, or they could be different ages, or at least ages as centaurs.
Right, okay, yeah. So not necessarily when they were made, but when they started, like, having crazy orbits
Yeah.
or... Okay.
Yeah. Some of them seem to be red because of the organic compounds which have been irradiated by the light, which has changed them in some way to produce the red colour, but yeah.
Right. Okay.
There are different colours. That is what can be said firmly.
We can categorically state they are different colours.
Yes.
Sometimes.
And there are probably different, like, multiple reasons, I think,
Yeah. I guess also, like, I mean, it's partly, like, spectroscopy. Like, if you can look at it and say there's some olivine in there, I'm very impressed because I kind of feel like I wouldn't be able to tell you, as a non-geologist, if you gave me two bits of rock, I'd be like, oh, that's a rock and that's a rock. They're both kind of the same colour. But they've, like, come about in completely different ways, for instance. And they're also rocks that look like very different, but are actually the same type of rock, right? They're just, like, a slight different composition. And that's with the rock right in front of you here on Earth, and you can, like, check, like, you can do all sorts of experiments, whereas these are sort of, not necessarily on the edge of the solar system, but, like, really very far away from us as observers.
I do think it's very impressive. Spectroscopy is an amazing tool and opens up a lot of science and progress, especially in astronomy. Although it's very useful in many, many areas of science. And I feel like it's, a valuable tool to many scientists. But I would say, on the other hand, to your having the rocks there right in front of you, you almost find yourself in the situation of being a solar physicist rather than a stellar physicist, where you almost have
Too much
data, and then you're trying to, classify or identify or whatever, and there are things that throw you off that you just wouldn't have to deal with if you didn't. Do you know what I mean?
Yeah.
I think there's a happy balance.
Yeah.
Probably somewhere between looking at a rock that's really far away in the solar system and having it on your desk. Probably somewhere in between those two, where you have the optimum amount of data. But yeah, it is amazing. I find it really cool. We can learn quite a lot about objects in the universe, not even just the solar system, by using spectroscopy, and it's very clever.
Yeah.
It's a really neat, part of science that we've understood to be able to implement that as a tool.
Yeah.
When all you have to do, you get some light from the object that you're interested in, and from what the spectrum of that light looks like, you can say, well, there's a peak here, there's a little bump that says that there is a lot of light at this particular wavelength. And there's another peak that says there's a lot of light at this particular wavelength. And therefore, I know that it has olivine or, lots of helium or something in it.
And also, what's extra crazy, the thing that I find amazingly crazy, is the fact that it comes out, you get the data, and it just looks sort of like random dots to some extent, because it's so noisy as data. And then clever statistics people come along and go, it's clearly a nice sharp thing if you just remove the noise through scary statistical methods that I don't understand.
Yes, because I had to... I once took a module where I tried to learn how to do this from more first principles. For a lot of people, you don't have to do it from first principles when you're actually researching, because normally, there'll be like a bit of code that within the group or, in the language that you use or whatever, that will remove the noise in the way that you want it to.
Yeah.
Because there's no point writing a bit of code to do that again and again and again and again, because what you're interested in is the science, right? So you do that job and then you get the thing out that you can identify the bits of, and then you do your science. Whereas when you're learning about something, you often have to do things from first principles to prove to yourself and the person teaching that you understand. I don't know.
Yeah.
Sometimes just because they're sadists, I think. But
yeah, definitely.
And yeah, it was pretty painful. I got it to work, but I didn't understand. I didn't feel like I got to the end of it and went, well, and now I have a solid understanding of how to remove the noise from this data and all types of data, because how you remove the noise depends on the data that you have as well. So
yeah. I was going to say, your lecturer would probably be like, it depends on the data, because then you'd use one of 6,000 different types of statistical methods, which all have their own variations. So depends on the data.
But I learnt a very important lesson.
Okay.
Which was, if I ever need to do that, I know someone who knows how to do it.
Well, that is very important.
And I can go and ask said lecturer, how would I go about doing this in this scenario? And know that I will get a very well thought through answer to that. But yes, you got to be able to remove the noise first. That is the tricky bit. Probably not everyone would agree with me, but that was how I felt.
So, you, Ro, wanted to talk about FarFarOut, which sounds like a movie.
Yeah, I just like its name.
Fair. Very
to be honest, that was kind of why I wanted to talk about it. It's got a cool name, which is cooler than its, it's more of a colloquial name, I suppose, like a nickname, but like a well-known nickname, which is far cooler than its other classification of 2018 AG 37.
It trips off the tongue.
Yeah. Which is a Centaur. And
Okay.
a distant trans-Neptunian object. Do you know how far away it was when it was discovered from the sun?
50 AU.
Higher.
60 AU.
Higher.
100 times the distance of the Earth from the Sun.
Higher.
1,000 AU.
Okay, not 1,000 AU.
Okay. So not that far out. Pretty close. How far?
132 AU,
Okay.
which is the equivalent of almost 20 billion kilometres from the sun.
Right. Okay.
Yeah. And it's a Centaur because its closest approach is thought to be within Neptune's orbit. So it's within the outer planets.
So Neptune's orbit
So-
is like just shy of, or about 30 AU, right? Something like that.
Yes.
So it's maybe 4 times as far out as Neptune.
When it
When it was-
discovered, which is, let's be honest, it's not going
Where
to
it
be any
still
different
is,
now.
pretty much.
But yeah. Yeah.
Okay.
It was first imaged on the 15th of January 2018
Nice.
by
A new year.
a bunch of astronomers. They were doing a sky survey at an observatory in Hawaii, and they were looking to find distant solar system objects, and the hypothetical planet 9, which we're gonna come back to in a later episode. But even though it was imaged in 2018, it wasn't noticed in the data until a whole year later,
Right.
January 2019.
I love that when you got data lying
Science.
around you like, wow.
I know, how lucky is that when you've got data coming out your ears?
I reckon spending January in Hawaii observing is probably not too bad.
No, I don't think it is too bad.
Shout out to any Hawaiians listening. Tell us, is January the worst month of the year to live in Hawaii?
Probably not. I imagine the worst month of the year to live in Hawaii is when all the tourists turn up.
Which might be January, to get away from the cold.
Yeah, maybe. Maybe
Maybe not. Maybe just go to California. Don't know.
But yes, the team were reviewing the data a year later when they noticed 2018 ADLI 37, which is not
Handy.
currently named that. The main astronomer doing the work at the time estimated that the distance to the object was about 140 AU, which I think is pretty good going.
Yeah.
Like, that's remarkably close. But anyway, they found that, and then they were like, oh, well, that's actually further out than 2018 VG18.
Oh, well, you can just see that.
Yeah, which was another object that his team had discovered
Okay.
a month earlier.
I guess his team are quite good
And
at
then
finding these
named
objects.
it, yes, I mean, that's what they do, right? Named it FarFarOut.
Right, okay.
So then he was like, well, this one's far out.
Alright.
So that was that.
I reckon I would have gone with further out.
Yeah, I think I would have as well. Although I kind of do enjoy that because I'm like, what happens when you find the next one?
Far out, yeah. Or is it far three?
Cubed out.
Yeah.
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 Because it's going to happen, right? It's inevitably going to happen.
It is. At which point...
But yeah, it's not FarFarOut. has not really been particularly well observed, really. As of 2021, which was the most recent I found, but it doesn't mean that there isn't more. It's only been observed 9 times.
Okay.
So, and being, far away from the sun, it moves pretty slowly. So, in the 2 years that we've known about its existence, it's not really gone all that far. So, it's kind of difficult to determine what the orbit is going to be like.
Right, because it could have gone like 200 million miles. I've got no idea, but like its orbit is massive.
Yeah.
So it's like a fraction of a fraction.
It's a tiny bit of its orbit.
A slither. If you drew a circle on a bit of paper, you wouldn't even be able to like.
You wouldn't even know it was a circle.
Yeah.
Yeah.
Be a dot on a page, and you're like,
yeah.
What's the circle?
Yeah. You could draw any circle, and.
Yeah.
Yeah.
And you got to kind of try and work out. Well, it was slightly. It was like a fraction of an atom on the sheet of paper, like that way 2 years ago. So let's project an entire circle. Tough.
Yeah.
Okay, so we don't really know
No.
for sure. There are high levels of
uncertainty. Yeah, and that also translates to, closest and furthest approaches as well. Not just to the shape of the orbit, but also what is the furthest it actually gets, and what is the closest it actually gets. But probably the period, is 1 year for it around the sun is about 700 years.
Right, okay. So is that...
Which is a pretty long time.
Is this then is the furthest out, it's far, far out. So is that further out than anything else that we've ever known about? Or is it like currently, do you know what I mean? Like, did anything used to be further out and it's come back in?
No, I don't know where they all are currently.
Why don't you know?
My brain trying to wrap my head around the question and then formulate an answer to that.
That's
I
fair.
do not know where every single object in the
why
solar
did you go to
system
university?
is. However, FarFarOut is the furthest out observed body.
Right.
So there are over 100 trans-Neptunian objects that have an aphelion or furthest approach from the sun.
So trans-Neptunian is just, it goes beyond
the
orbit
Neptune.
of Neptune. And this goes beyond the orbit of Neptune, as well as also inside the orbit of Neptune, we think.
Yes.
So it's a Centaur.
Yes.
And trans-Neptunian object.
Yes.
Unless you have a different definition of Centaur, but whatever.
Yes. There are over 100 other trans-Neptunian objects that go further from the sun than FarFarOut.
Right.
Goes. And also, many of the comets are currently much further away from the sun as well.
Okay.
So, some of which would be Comet Donati, which is over 145 AU. Caesar's Comet, which is thought to be more than 800 AU from the sun.
Okay.
But none of these objects are currently observable. So we can wait for Caesar's Comet to come back to us, and we'll see it again, or Donati's Comet, or any other of those comets that have really large orbits. But we can't currently see them.
Right. So there are some things that we can see right now that we know would go further out than FarFarOut would, but they're not there at the moment. And there are some that do go further out and are further out.
And we can't see them.
We can't see them, but we know that they'll be back again at some point.
Yeah, we have object permanence. We're aware. Just because we can't see it doesn't mean it's not there.
Right, okay.
But we can't see it.
So it's the furthest visible thing, or the furthest thing that we can detect currently,
Yes.
but it is not the furthest known object,
No.
as it were. Okay. And that's those comets, which then come in closer to the sun.
Yeah, and then
which
can
is why
see them
they're
again.
comets.
Yeah.
So do we
Really, we don't know very much about FarFarOut.
Right. Apart from it's far out.
Yeah.
But we don't know for sure how far.
No.
And yeah, okay.
Or how it's going to get. I was going to say here, but it's not coming to Earth, but you know what I mean. Yeah. Yeah.
Okay.
We know it exists. We have observed it. We've got photographs of it.
Okay.
We know it's maybe about 500 kilometers wide.
Okay.
So, then that's pretty big.
Yeah.
Which helps it to be more visible to us as well.
Because it's got a bigger surface area, so it's got more of an area to bounce light back to us
Yeah.
from the sun.
And to help us, I guess, it's pretty bright.
Okay.
Its surface is probably very icy, so reflecting a lot of light to us. So it's very bright, which helps us see it. So it's big and probably very icy. Other centaurs or objects might not then be as easy to see. It might be that we can't observe them once they get beyond 100 AU or something. Whereas we can observe this
Yeah.
at 130 AU.
And if it's less icy, then it makes it difficult because it's not bouncing as much light off.
Yeah.
Kind of thing. Okay. And when you say it's bright, I guess that means it's bright for things that are out there, I suppose.
Yeah.
When you're talking about the
It's
falling
not
off
like it's not like the sun.
we're not looking up into the night sky and seeing a really bright star.
Yeah.
It's actually far out. It's
Yeah.
Yeah.
It's just bright for what it is. Everything's relative.
okay. But FarFarOut isn't a centaur in name. It's not like there was a centaur called FarFarOut. So what's he doing there? Why is they not named after?
Yes. It's not. Not following the appropriate IAU naming schedule. We don't really know its orbit accurately. We don't really know much about it properly.
Okay.
So it can't be officially named until it is better known, really.
Right, okay. Is that because we don't necessarily know how to classify it? So, not necessarily in this case, but like in general, do people like to be like, we know exactly
They
what
like
it is,
to
so
have-
what naming convention we should go down?
Yes, and then it'll not do that at all. Yeah, I think people feel more comfortable when there's more data and stuff, and also it just takes time for things to happen in reality. Committees and everything, it doesn't. Things can go a long time before having more official names.
Yes. Yeah.
Far longer than you would think would be the case.
I guess given how far out it is, and tracing that circle, it's going to be like hundreds of years or something before we're able to name it.
Yeah, I'm not quite sure what they're looking for, waiting for. Presumably the data that they're waiting on can't just be what does the orbit look like. We can only name it after that because they're going to be waiting a long time. But it might be that, with some more data on it, they might feel more just comfortable in general, classifying it one way or another and therefore giving it a name or not. And also they probably will rely on more theoretical based work. But even that requires some sort of input data, so... Yeah.
So if you had to name a new object after a centaur in any sort of fiction or mythology, what would you pick?
Let me think about that and get back to you.
I can't think of any centaurs in anything ever.
I don't know.
I don't
Maybe
feel like they crop up that often, do
maybe
they?
I'll bring one to the table next week. I don't think I can name any off the top of my head.
No. Such a weird sort of naming. Well, if any of the listeners have any ideas of centaurs to name things after, we can check if they've not been taken. Let us know. And
see you next week.
So that just about wraps things up for this episode. Please, can we encourage you to subscribe to Through the Telescope wherever you find your podcasts, and if you like, you can leave us a nice positive review as well. It really helps the show and it makes it easier for more people to find us.
Feel free to send us any comments, questions or suggestions of things or people you'd like to hear about or from in future episodes. Or perhaps to put yourself forward to chat about your own astro research or experiences. As always, you can find us on Instagram at Through the Telescope Podcast, or you can find me at astrophysicist_Rose. You can also find us on Twitter at The Telescope Pod, and you can contact us by email at throughthetelescopepodcast@gmail.com.
And with that, we'd like to thank you very much for listening, and we look forward to seeing you again next time.
Bye.